All right. How you guys doing? Doing well? Good, good. All right. So today we're pretty much done with the disinfection stuff. So today will be more topical on disinfection technologies, a bit of a research talk for you. I decided to do some solar disinfection. So if we think about what kind of technologies can we use if we want to use sunlight, or in general use light to activate a disinfection process. So what we're going to discuss in general is a mixture of how well does sunlight work by itself, and if we add some material that absorbs sunlight, what kind of impact does that have? So it'll be a few different topics. You'll see that it kind of connects with the general reaction kinetics type of things. And then we'll go a little further and say, well, how does it work with a particular, if we have some solid material, do we coat it on the walls of a bottle, and what kind of impact does that have, or things like that. So general theme here is SODIS. People will often use that term, SODIS, for solar disinfection. And then technologies, opportunities to improve on it, kind of what goes wrong and what can we maybe fix. So the basic principle of SODIS is to put your water in sunlight and let sunlight be the best disinfectant. Now, as I mentioned last time, turns out sunlight itself is not a great disinfectant all on its own, especially if you have a colored plastic bottle like mine. It won't work too well. Most of the UV is going to be absorbed by the plastic and the dyes in the plastic itself. Now, fortunately, the very typical PET bottles, that's polyethylene terephthalate, that's what most Coke bottles are made out of. Probably these Panera cups, I'm guessing would be PET. And it's pretty transparent to the UV that the sun does provide. So putting a bunch of Coke bottles on a roof or a thing like this will actually let some of the UV through, and you'll get a combination of heat and UV light. And if you leave it there for long enough, that will have some disinfecting ability. Now, of course, that's not going to be anywhere near as fast as if we had, like we talked about last time, the germicidal stuff, the stuff that really damages DNA like real quick. So we need to account for that and the reaction, since it's a slow reaction rate, to give it enough time, right? So that becomes a big part of the problem. So in order to achieve some disinfection, and I mean some, it's not actually all that amazing, we need to wait probably 6+ hours. And that has to be in pretty much full direct sunlight. And we need it to be good quality sunlight, meaning if we're too far from the equator, we're kind of out of luck. Now, I guess a caveat or a counterbalance to that is most of the regions that might be considering SODIS as kind of a last-ditch effort to treat some water, they tend to be closer to the equator, right? We don't have actually too many very poor countries that are lacking water infrastructure far from the equator for whatever reason. So, but you need that. So if you're in a very cloudy region or something like that, it's not going to work too well. And just another thought for you, you might consider, well, why not just boil the water? Wouldn't that be a little easier and faster? It turns out that if you are destitute to the point of needing any method to clean up your water, boiling will be very expensive because it takes a lot of energy to heat up water to that amount, and fuel in many cases is expensive. It's also likely that you're going to be harming your local environment if, again, in that sort of situation, you're cutting trees or something to find some fuel for your fire. So it really is a potentially positive aim to use sunlight instead. Okay, so we talked about last time the UV wavelengths, the UVA, B, and C. We also said that UVB can be used and we get a bit from the sun. It's just not a lot gets there. So if we use the right kind of bottles, if we have full direct sunlight in the middle of the day, the kind of sunlight that would, if you spent all day with no sunscreen, you'd definitely get burned, right? Or a lot of people would. That kind of sunlight is what we're looking for to essentially give the microbes a sunburn. And when you do all of this, you'll get something like a 2-log reduction in bacteria. So typically, we might expect something like 99% of bacteria. Maybe killing off some viruses as well. Just a reminder, this is 99% in 6 hours. So if we compare that to that germicidal light, if we have the same intensity of UVC, the germicidal stuff, even for a few seconds, that's going to do a much better job. So it really is a big difference in how much of this light is actually causing a direct impact. There's a very few photons within the solar spectrum are causing that harm directly. There's going to be some indirect stuff happening that we'll talk a little more about today, but that's maybe something we can enhance, but not something we can rely on with just sunlight. So I mentioned last time I have this cool graph. This is actually data when I first got here in 2016, one of the first things we bought was a little portable radiometer, which measures light, and you can point it at the sun and see what the sunlight looks like in terms of the wavelength. And then there was an eclipse in 2017, and so we said, hey, let's just bring this outside and watch what happens during the eclipse. So it was just kind of a fun exercise. And the lines here, we started, I think, at just after noon, so 12:20. And this was kind of the solar spectrum before, kind of the default amount of sunlight. And this is kind of arbitrary units on the y-axis. We could probably convert this into some sort of energy unit, but this was just the instrument's reading for now. But what we can see is that it was dropping, right? And for the eclipse, it's not really going to change the type of sunlight we're getting. It's just going to change the amount, right? So we're not expecting any change in the wavelength. It's just kind of shaded. So we can kind of see that drop and then raise back, and that's pretty neat. But you can, if you look closely, right about here should be the 300 mark, something like that. So that means between, like, anything that was in this region is kind of the UVB. And then anything between 400 and 320, this is kind of the UVA. So you can see pretty clearly, even for the full sunlight case, and this was, I think it was probably September, maybe October in 2017. It was a sunny day for the most part, so we've got some pretty good light, and we do have some UV coming through. It's just not nearly as much as the bright yellow and all the other colors that we're getting. So just to kind of show you what we're looking for, we would expect a bit more intense in the middle of the summer or perhaps closer to the equator, but this is kind of the middle of the day. We can see it. We can see that UVB, definitely no UVC, thankfully, and that's what we're really relying on for the most part. Now, the rest of the light can also generate a bit of heat for us, and it turns out that 6 hours in the hot sunshine will heat your bottle decently well, and that extra heat can stress out the pathogens a bit. So it's not at the boiling level, but it kind of helps make them a little more vulnerable to disinfection. We talked about this one last time, just kind of showing the germicidal effectiveness. So the tail end of the solar spectrum was coming down like right here. And so the little overlap is this little segment, right? And that's the little bit that's a direct DNA damage. Occasionally a photon, like there's not many of the photons coming like that, and occasionally they'll be absorbed by DNA and cause the damage, right? So that's why we need a lot of exposure, long time, to give that the odds for that to happen. Okay, a few other things that can affect it, and this is probably too small to read, so don't worry too much about it. The temperature I mentioned. If your water is cloudy with particles, it's going to scatter the light. It's going to shield the microbes. So that's going to make it a little worse. If you have clouds, that's a problem, right? You're not getting nearly as much sunlight. Of course, rain, which would also cool it off. And like I said, the latitude. So we could take a look at different organisms. That's what this chart is showing. And I think it's showing kind of the potential disinfection amount if you had, and the disease that it's corresponds to, in the most ideal solar disinfection scenario. And I think it's a little exaggerated because some of these numbers are a little too many. Oh no, that's at 40 Celsius. So if you get it pretty hot and 6 hours, I think this is the max you could possibly expect. But I've also seen some things that indicate this probably doesn't even get that much. So, but you could look at the different types of organisms: bacteria, viruses, protozoa, and some of them, at best, you get a little bit of a reduction, right? So some of them, like Giardia, says rendered inactive. I don't know. I think that probably wouldn't always be the case. The crypto says with over 10 hours of exposure, maybe you get it. So there's maybe a consideration there. I've seen other sources that say 99% is kind of the best you can imagine. Okay, so here's a bit more on the kinetic side of things, as from a paper, kind of determination of thermal inactivation of microorganisms. So if we want to know how much does temperature impact them, like if we were to just boil them or to generally heat it, we can track how quickly that happens given some temperature. So the one on the left here, this is survival. This is a log scale, so right here would be 99%. So in that case, if we read closely, this is going to be at 105 degrees Celsius, so a little above boiling point. If you get your water above boiling point, then it's going to take about 20 seconds to reach 99% inactivation. You could look at the same type of scale, and as you see, we could find kinetics here and find a K rate constant for a given temperature and pathogen, right? So if we were to do that, we looked at this last time, right? Finding the kinetics from the data. So we could certainly do that, and we could do that for all sorts of temperatures and all sorts of pathogens. And this is why if you ever have a boil water advisory, or if you're going hiking or something and you need to boil water to drink, you don't do it just for like, oh, it boiled, we're done, right? You boil it and let it keep boiling for 5, 10, 15 minutes, right? Because first of all, 99% might not be enough. Second of all, this is at 105 Celsius and water boils at 100 Celsius. So even at like, even if you're not hiking in any mountains, because if you're up high elevation, you're even lower temperature when the water boils. So even if you're at sea level, you're not even getting this fast. And it would take 40 seconds to get a 99.9%, excuse me, 99%. So you can imagine that the boiling water, it's effective, but you need to make sure you give it a long enough. This next figure here says 72 Celsius, and we can see some of the organisms, and this is a time scale, also seconds. So some of them are pretty susceptible, but some of them are just a small change over the time scale of seconds. So maybe bringing them up to that temperature, some organisms will just die, and that's good. But some of them are going to hang on and live for some while longer. So all that's really to say, like the temperature is going to make an impact, but depending on the temperature we can achieve, it's not very likely we can get 70 Celsius from just sunlight unless we're doing like a solar concentrator, having reflective mirrors and concentrating into one spot. And even then, we'll probably need to heat the bottle and then let that transmit it into the water. And at some point, we might have to worry about, is our plastic bottle going to melt? So some of that's simply not super practical in most cases. So when it comes to just the solar part, we've got a few pros and cons, right? We can use just your plastic bottle. That's great, which means there's almost no cost. That's typical even in very resource scarce settings. Coca-Cola makes their way everywhere, right? And so there's almost always some of those types of bottles around. It's pretty easy to understand, and you can kind of get a feel for the sunlight. Without any knowledge about bacteria, you can kind of get the feeling that sunlight can clean stuff, right? It's sort of a general impression you get. It's very bright, it gets hot. You could understand that this is, if there's something dirty, maybe that'll help. So, and that point is actually very important for considering how to teach people how to do this stuff. Because in many situations, if you're working in a developing context, many of the people needing this may not have much access to education. So they may not even know what a germ is, right? They may not have that conception. They may not know that there's a correlation between dirty water and illness, okay? So when it comes to aiming to provide engineered solutions, we also have to recognize that the educational component, how acceptable is this, how reasonable does it sound to somebody, is quite important. Okay, so some of the cons, your inactivation is pretty limited, perhaps even to 90% of bacteria. Maybe we have a better case, maybe we can get up to 99, maybe further. But a lot of times we're not getting a whole lot, and there will be some that are more resistant than others. It's not very effective versus some protozoa, some viruses. Again, some will be susceptible, some will not. It's a lot of labor demand, and if you really wanted to drink a bottle of water, do you want to wait 8 hours for it? Or do you want to wait 6 hours and then drink it while it's still hot? You know, at some point, maybe make it into a tea and then you're going to boil it, so might as well just boiled it, right? You're just thinking about the prospects of using water that has sat like that. You have to plan ahead. It's not, you know, if you do that during the day today, what are you going to do in the morning tomorrow for a glass of water? You know, there's a lot of reasons that it will become less and less practical as we consider the implications. There's also a factor that it's not a very aspirational target, right? If we want to bring in some sort of technology, some sort of improvement for people's livelihoods, one thing that's, you know, again, can be important is to provide a way for people to look to what they could achieve and do for themselves in terms of making their lives better, right? And having their own ownership and own initiative there is really important. So if, for example, if you can set up a system where they can, a group of people can dig their own well or something and participate in that and get clean water from that, they could take a lot of pride and ownership there, and it would be a little bit more aspirational than, oh yeah, you're going to have to put this on your roof every day and good luck, you know, and then the water's going to be hot and taste like plastic. So there's some definitive limitations there, even though the concept of, hey, let's use sunlight to disinfect our water, it's good on paper, right? It sounds good. Okay, so then the question becomes, how can we enhance that? And this is where some of the more fancy material science and research comes into play. And of course, there's always a question of, can it be practical? How could it be practical? So we're going to talk about those pieces as well. But the basic principle here would be, if we take sunlight and then shine it on some fancy material like a buckyball, the Buckminster fullerene, those happen to accept the light very conveniently. They get excited, and then they can transmit that excitation to an oxygen molecule, which makes that oxygen highly reactive. So then that oxygen is going to act like a very, very strong form of chlorine, and then go and do our disinfection. So in that sense, if we use light and then the oxygen that's just in the atmosphere and therefore in the water, adding that material is now catalyzing the formation of a disinfectant. So this is a very attractive concept to go and kill our bacteria or viruses. So on the technical sense, this is oxygen that we would breathe being transformed into what we would call singlet oxygen, which is very reactive. Technically, if we want to be really fancy, ground state, regular oxygen is in a triplet state, which is kind of weird, but it's what it is. and this version is the microbe killer, right? This is a, we could call this a chemical disinfectant. This happens to be what I did my graduate work on, so I could talk your ears off on just that in itself if you wanted, which I'm kind of doing today, but I'll try to keep it mostly general. Okay, so another thing we could use, another material that has that property, is actually a lot of our food coloring dyes. A lot of dyes in general have this property where they can absorb the light, and hopefully we can get visible light or UVA light to do the trick. Fullerenes can absorb just a little bit of visible light, but they're pretty good with the UVA range, so it's still practical for sunlight. You can modify them a little bit and improve the visible a little more, but a lot of these dyes can do that quite well. And so one of the interesting challenges that the fullerenes that they face if you wanted to use them is, one, they're kind of expensive. Two, they don't like to be in water because they're all carbon, they're not charged, so they just try to avoid being in water in some sense. They're hydrophobic. These dyes, however, are a little better. And part of the potential challenge for something like a fullerene is if they don't want to be in water, then they have to be on some surface. How do you keep them on that surface? How do you expose all of the water and the light to that surface and have it all mix and everything? There's a few challenges there to deal with. But if you could just add some dye that is like a food coloring that is presumably safe to drink, if you're going to add it to your food, maybe you could add it to your water. And it turns out this is a project that kind of followed mine after I graduated. And I was jokingly jealous because I was like, oh, you made it actually practical now. Now it actually works. Because then you could add the dye into the system, expose that to the sunlight, and get really effective singlet oxygen production, meaning it's now going to have that catalyzed disinfectant. I think I have another slide on that. There's a couple caveats, so in case I don't, I'll just mention now. There's a couple caveats because the dyes themselves could degrade, and there's a question about, well, when they degrade, are they becoming toxic byproducts? It's possible. There's a nice thing about that. Let me stop and spell a word real quick. So there's a couple questions. One is, are they toxic? Because sometimes they will have iodide in the molecules themselves. Is that going to be toxic? So I minus. Maybe it could be a benefit if there's iodine deficiencies. That could actually potentially be a helping thing. But on the other hand, kind of a positive, you can use as an indicator. If the dye has had enough time to degrade to the point where it's done a lot of this photocatalytic activity or photosensitizing activity, then you know your water's clean or clean enough because it had enough time, it created enough of this radical, these reactive oxygen, to destroy itself. Therefore, it's surely had enough time to destroy the bacteria and viruses around. And it turns out that part of that study showed just that. So the color can then be an indicator directly. So as it fades, might take maybe 10 minutes in the sun, then it's relatively disinfected and ready to drink. So you're going from something like 6 hours to something like 6 minutes, which is another great thing. So I'll say 10 minutes. So this process could accelerate it to the point where it's only a few minutes. Okay, so there are other similar processes. These are actually a little more popularized, at least in the research. Photocatalysis is very similar, and in essence, you're shining light, activating some material. The chemistry from there, the photochemistry is a little different. You're actually giving off an electron, and so that changes a little bit of what happens. But at the end of the day, you're creating these reactive species that can go and destroy stuff. These ones in particular, typically they are heterogeneous, meaning we have a solid surface mixed in with the water in the liquid phase, whereas the dyes are completely dispersed, they're dissolved, they're homogeneous. So that means we do have to deal with some surface, and most of these radicals are going to be at the surface. So the hydroxyl radical here, for example, this is known as, in the atmospheric chemistry, as the atmospheric cleansing agent. It's a very, very strong reactant. This is part of what's formed when UV is absorbed by oxygen and ozone in the atmosphere, and you get this really, really reactive stuff. It takes away the UV light, and this will then go and react with just about anything it can find and destroy it or recombine with it and create something else. This is actually why ozone is formed in large part, because of this type of activity. Just that strong UV coming in, hits the oxygen, goes through a bunch of photochemical pathways, and you end up with some ozone, and it repeats. So the ozone layer then is just naturally formed and reformed in that manner. The concern some years ago was certain chemicals could catalyze the destruction of ozone, and we might have some lack if we had too much of those catalyzing chemicals. So these hydroxyl radicals, they react so quickly that they only live a few nanoseconds. So that means they can't really travel very far away from the surface. So we kind of have a mostly surface phase issue. So their lifetime is about 5 nanoseconds, plus or minus a bit. And that means the travel distance, a few nanometers on average. So that presents us a little bit of a challenge, because it's not so nice as chlorine that's just going to be well mixed throughout our system. And since we have to have a solid particle here, or a surface, then we need to kind of have that surface in contact with a lot of water, meaning we need a lot of mixing or some smart design for a system to allow a lot of water exposure. So putting these together, some applications for each piece. Of course, disinfection, like I said, but we could maybe even do one further and destroy some pharmaceuticals or pesticides or things like that in water or wastewater. So there's a few places where we'd like to apply these photocatalytic materials or the photosensitizers, in addition to to drinking water. And notably, we don't have to use sunlight, right? We could engineer a system and blast it with UV light. We could use sunlight. Maybe we could do some sort of solar concentrator. But at the end of the day, we can use these photocatalytic processes kind of like an advanced oxidation process. So going beyond just the SODIS realm, we can target industrial chemicals or something like that. So you can imagine caffeine here, this molecule, if a hydroxyl radical attacks it, it's going to break apart some bond somewhere, and ultimately drive some organic molecule like that towards CO2 and water. It's combustion reactions, essentially. So if we take oxidation to completion, then in this case, there's some nitrogens there too, so we might get something like nitrogen or nitrate or nitride or something. Some mineral type, we would call this complete mineralization. If we take caffeine and just blast it, it's as if we incinerated it. That's kind of the same deal. Okay. So I provided this as an example, I think last time, or maybe the first lecture on this. This is an example, real data from disinfecting a virus using the single oxygen method, doing the light to the fullerene, transmitting that energy to single oxygen, and then that goes and destroys our little MS2 bacteriophage virus. These guys look like little spheres, little molecules to find and attack their cells that they would host, right? So the single oxygen then is killing them rather quickly, and it was pretty impressive that we were able to do that with very, very small amounts of our fullerenes. And in part, we believe that was because the fullerenes had a positive charge, at the surface, and these guys had a net negative charge at the surface because we attached some special stuff to the fullerenes. Okay, if we take a look at photocatalysis, it actually doesn't typically work quite as well. So this is using a common photocatalyst, TiO2, titanium dioxide. You'll actually find titanium dioxide in a lot of places. There's a good chance it's in the paint here. It's a pretty much all white chemical because it doesn't absorb visible light. It absorbs UV light quite well. And so what happens is if you shine light on it, then it's going to reflect back nice white light. It's kind of a mixture of all the colors from your light source because it's not absorbing any of it. So you'll also find it, therefore, in things like powdered sugar donuts. So you've actually eaten quite a bit of titanium dioxide in your life, chances are. It's in a lot of sunscreen lotions, that and zinc oxide, again, because it absorbs UV really well. Now, if we set it up and put it in water and get small particles, then we're generating a lot of radicals, which you'd think could be a bad thing, but in the case of sunscreens and things, they're using a type that doesn't tend towards that end. So it's absorbing the light, but not generating radicals from it. So if we use the different structure, different type of it, then we can generate some radicals and then apply it. And you see here we've got, action on the scale of 3 to 5 hours, doing a pretty good job cleaning up the water. And this is with I think this is UVA light against some E. coli. So E. coli are going to be a little bit resistant to it because you have to oxidize their lipid membrane and you have to destroy a lot of them before they're going to be sensitive to it. So it took some time, but you can get pretty good disinfection with kind of high concentrations of TiO2. So 0.1 gram per liter, so that's 100 milligrams per liter up to 2 grams per liter in a kind of a batch system. You'll also notice normally we'd expect kinetics to be pretty linear on something like this. We've seen this a lot in the class, right, where we start at 0 on a log scale, and if it's first order, then it should be a straight line. But here, they become a straight line later, but there's sort of a lag phase where the bacteria are sort of resistant to it. You can expose them to some oxidation for a little while, they resist it, and then finally you overwhelm it. We actually see that in UV sometimes and other disinfectants, but assuming we get past that lag phase or the shoulder there, then we typically get linear kinetics. So I haven't shown you too much of that for the purposes of our class because I didn't want to complicate things too much. So we might call this a lag phase, followed by approximately first order we'll say decay. Something like that. Okay, so a few years ago, one of my former lab mates did my graduate work, and he was there as well. He published an opinion paper saying, well, where are we going with all this? There's been probably 1, maybe 2 industrial scale applications of photocatalysis. We've done all this research, we've known about it since the 70s, and nobody's using it. What's up with that? We're always talking about it, all the researchers are wanting to study it, but is it all hype? Is it just going nowhere? And it's a very good concern and criticism, because if we're doing all this research on it and it's never practical, why even think about it, right? So my hope is that there may be a path forward, at least in some aspects. So maybe it's not going to solve the clean drinking water issue, but perhaps we can design materials a little smarter than we have before and design a reactor in particular such that we can achieve something useful out of it. So to practically apply something, we actually have to solve a few different constraints And a lot of researchers have just been studying like, okay, can we make this material absorb more visible light? That's a good thing to think about, but it still might not make it practical. So a few things that are pretty important. Yes, that use of visible light, but also the availability of light. Can you get the light to your material if you have put it on some structure, right? If you're gonna flow water through a system, have a flow through system, you're gonna anchor your photocatalyst onto that structure somewhere. And then can your light get to it in addition to the water getting to it? So if you make some complicated like flow through system where you've got lots of pores and things, can the light get there? Well, you might have just shaded it all with your structure, right? So that could be a problem. Diffusion limitations, talked about this, those radicals react so quickly, they're not going to diffuse away too far. So we have to get the water and the bacteria, therefore, close to the material and overcome those limitations, in large part because our disinfectant, just like chlorine, we need a contact time. We need the concentration of our disinfectant, in this case, maybe some sort of reactive oxygen species, hydroxyl radicals or single oxygen, and they need to be in contact with the bacteria or the virus for some amount of time. Well, when those radicals live for so short amount of time and they're not filling the entire reactor, we don't have a well-mixed system like we often assume for chlorine, that becomes a challenge. In addition to that, if we have other junk in the water, they might consume the reactions, right? In the case of chlorine, we didn't really talk about this much, but chlorine will react rather quickly with certain metals. So if you pull up groundwater and it's got a lot of reduced metals, the chlorine itself will react with them, oxidize the metals, which might be a good thing, but that consumes the chlorine really, really quick before it has time to react with our pathogens. So and hydrogen sulfide is a good example of that as well. So when we are using our radicals, if we have organic materials that we don't care about, like that dissolved organic matter stuff, that could be a big problem because it could be reacting with all of our radicals before the radicals have a chance to react with the viruses or things. Okay, and finally, we need to do all of this and solve all of this while also keeping our catalyst material or our dye or whatever in place. So the dye case, it can degrade over time, so maybe we need something stronger. The fullerenes are pretty good for that. They don't really decay so much, but you'd need to attach them somewhere and make them happy to be in contact with the water. And then you need to do that while also making sure light's available and the diffusion situation is solved. So it becomes quite a complicated task to try to piece all of these these different things together. Okay, so little diagram here just showing how far things might diffuse into water. Like I said, hydroxyl radicals here, they have a really strong redox potential, meaning they can oxidize a lot of stuff and destroy it, but they only diffuse a tiny bit of distance into water. We also have something called superoxide radical anions. These are a little better, but overall pretty similar in terms of they don't really travel very much more than maybe 100 nanometers. It's not a lot of distance. Our single oxygen is getting to the point where it's a little better, maybe 1 micrometer, 1,000 nanometers. So that's getting to a point where it's getting a little more practical in terms of sending the disinfectant out to do the cleaning. Hydrogen peroxide is another one we could consider. We could actually apply that directly as a disinfectant. It lives for a long time and can disinfect, but maybe we don't want to be drinking hydrogen peroxide directly, so it's another consideration there. Do we then let it decay, or how do we handle that if we're producing a lot of it? Okay. Part of a recent study I was involved with was looking at that quenching between this organic material and the radical that we're trying to produce. So I've got a few graphs here just to show you what it looks like to study this sort of thing and how we're using the kinetics that we've learned about in class. So what we have here is the destruction of this molecule, which is PCBA, it's parachlorobenzoic acid. That's a good representation of some contaminant that we might be trying to destroy chemically. Then we've added some different wastewaters in different amounts. So ultimately what we're doing here is we're checking the kinetics across lots of different cases and making a comparison that's going to let us see to what extent does the competition happen at the surface of the catalyst versus out away from it. So we collected a lot of data in order to make plots like these to say, oh, okay, if the change in our amount of DOM, that wastewater organics, if we're changing that on the x-axis, how does that affect the rate at which, the rate constant for our destruction of this guy? And so in some cases we see it actually improved it a little bit, meaning that the organic material is probably pulling our contaminant closer to the surface. Most of the time it makes it worse. And so we checked different conditions and we're checking to see how are the kinetics affected by it. Ultimately what this research was aimed at was to figure out, can we improve the performance or at least prevent the scavenging by manipulating how the target is interacting with the surface compared to all the other junk. And it turns out that in some cases we saw some nice improvements like this. So while it's still a big challenge, there might be a route forward, seeing that in some cases it's productive if we tune our system correctly. So that's kind of on the quenching side of things. On the catalyst retention side, there's kind of another question. Can we keep the catalyst on a surface and make sure it's retaining its activity? Can we reuse it? Is the catalyst lost? All of those types of things. So we can imagine if we had a slurry reactor where we just have a bunch of particles, photocatalysts, suspended in solution, and we're pouring in some wastewater that needs to be treated, we're shining the light on it, we're mixing the whole system. That would be an easy way to get the system well mixed, solve the diffusion problem, but we have to capture the catalysts. And so what we would have to do is have some sort of a membrane afterwards. And at that point, if we're adding a membrane there, why not just filter the stuff? At some point, maybe we can destroy the smaller chemicals, and so maybe we can find a time where that's convenient. But probably it would be better to just filter. And if we start adding this natural or otherwise dissolved organic matter, could be interfering with the system, could be a problem. So one idea would be to use a membrane in the first place, and any of those targeted molecules that are coming out, the small molecules that pass through the membrane, could then be captured right next to where they're coming out or destroyed by photocatalysts. So this was a neat project where we shine light on the outside of a membrane, load that membrane with photocatalysts on the outside, so as the water makes its way through, the water's heading out, these little targets are being destroyed right as they're leaving the pores. And that's a pretty neat idea because you've solved your light management. The light is making it to the surface, and you're getting your liquid and your targets then really, really close to where the radicals are being produced. So perhaps it's not enough surface area, and again, you're still also paying for the membrane and all that, but it can remove some of the organics that are problematic, that would be quenching, and let you target the small things. So we had a project, and we studied the disinfection of human adenovirus 40, which is a stomach virus, and it turns out that the filter itself would remove some of it. The filter we were using UV light in this case, but no photocatalyst, didn't really make a difference. But then when we added the photocatalyst, we were getting a bit of a boost in disinfection. So even for viruses, it seemed like it had some potential there. So this is a slide I kind of already talked almost about all of this my point is to say there's a lot of different factors, and solving those all at the same time is really the important part. I also have this funny picture. This is my PhD advisor. He drew this artwork of himself for one of these papers. It was kind of reviewing and critiquing what's up with photocatalysis and where are we going with it. So he's a fun guy. Okay, a couple potential solutions then. We could also consider using, and I like this one if it's feasible. I'm not sure it's feasible, but to take fiber optic cable, which transmits light very well, remove some of the coating and replace it with a photocatalyst, and then dip that in water. Because then you've got your light transmitted to your photocatalyst, and as the light would normally bounce off, some of it probably still will, but then you're also activating your catalyst that's loaded right here. So you removed some of that cladding, coated it on there, and you have good light transmittance and hopefully good surface area. Yeah. So it's a good question, and I'm not actually sure. I've heard mixed opinions. I've heard some people say, in order to shine a light and get most of that light into the fiber optic cables, that itself is inefficient. So you're never going to get a good efficiency for your light delivery. But I've also heard somebody say that, well, if you get a nice lens here or polish it properly, then it works pretty well. So I don't know. It's always been something that I've kind of wanted to study and get into. I just haven't had the chance yet. So that it's in my opinion, it's something that we can probably get a solution for it, and it seems like a pretty good opportunity because you're not going to waste any of your photons. They're going to just bounce back and forth until they're meeting the spot where you want them to act, and then you can coil a lot of that fiber optic. You can actually make plastic fiber optics, by the way. So the standard fiber optics is glass, and the cladding makes it not fracture, so it becomes flexible. Like a thin piece of glass will actually be flexible, except without any protection, it'll just crack. Right? But if you give that protection, it can actually bend safely. Now, I say that, but if you ever work with fiber optic cables, make sure not to bend them too hard because they will crack. But they are technically flexible if within some practical limit. So this is one of my favorite concepts. Very good question there is like, okay, why not? Well, I'm not positive, but perhaps that light source issue can be solved there. Another possibility would be to use some sort of a flow-through reactor where it's just kind of a thin film, like a channel, and you could have a plug flow system this way, shining light, and have your catalyst supported all along this little channel. Do something like this. And this is from a paper where somebody was saying, oh, we can use single oxygen in this case for a chemical synthesis method that required single oxygen, and we could make it a continuous flow system in this manner. So could also be for disinfection. Pretty interesting idea. Probably not a lot of flow rate in that case, right? So that if you have to have a thin film of water, not a lot of flow rate there would be a challenge. Probably my the most promising so far is some work I've been doing with a professor in chemical engineering, Kevin McPeak, and he's been working to develop a catalyst support system that has kind of two layers of porosity, where we have a transparent support. So we take silica, which is kind of quartz basically, and we take quartz fibers into like a felt. That in itself, water can flow through, so it's kind of porous on a large scale. And then if you treat it properly and then load it with the photocatalyst, you can get smaller pores within that photocatalyst clusters, which is kind of what the electron micrograph images are showing here. So we've got a dual porosity of some sense, and then you could flow water through that whole system and shine light on it and get light through the whole system. If you made it too deep, then of course all that TiO2, all the catalyst is going to absorb all the light eventually. But in a thin enough system, or if you control the depth properly, then you can get a system where it's almost going to act like a filtration column of some sort. but also with that light action at the same time. So I think the way forward, and we've got some really promising results with that system, but ultimately the way forward is some combination of adsorption where we are intentionally letting our target stick to the surface and that photocatalyzed system. A lot of people to date have been trying to do something in like kind of like a UV dosing reactor where it's just like bulk solution and just all supposed to happen quickly as water's flowing through. I'm of the opinion that we have to take it to the surface and then get a surface reaction in addition to that photocatalytic reaction. So that's pretty promising. We've got some good results with hydrogen sulfide or HS minus, removal, oxidation by that. So there's probably going to be some applications, at least I hope, in the future once we can piece all these spots together. Now, it might not be that we get solar disinfection up to speed to the point where we have here, add this and it fixes all your water. Maybe that doesn't happen. Maybe we get a dye molecule that's perfectly safe and we can study that further. That could be quite exciting. But there you have it. That's a good overview of some of the technologies I've worked with, and I think that's all I have. So any questions, curiosities? Okay, so next time I will introduce kind of the wastewater regulations, and then the lecture after that will be exam review. Then we'll have the exam. I did have one question come to me. Somebody was thinking about the exam being on voting day. I apologize for that, but there is still early voting for, at least for Baton Rouge, East Baton Rouge. So if that's something you're interested in, make sure to check that out. Okay, so I'll see you guys on Tuesday.